I want to talk a little bit about work in isotropic turbulence from the point of view of maybe an astrophysicist or a engineer who really wants to know things about shear flow, convection, for example, and yet has been persuaded for reasons he may not understand fully to study isotropic turbulence as a simple, or the simplest possible candidate on the computer on theoretical basis also for turbulence to exist, although in some ways it does not really exist. So how do I get this to go? I see. There we go. So anyway, let's consider some variable x, which will be the temperature or the velocity field. And we split it, of course, in the average part, denoted by the angular braces, and the fluctuation part, usually denoted by primes. So the starting point of this is to assume that we can know the set of moments of low order without paying very much attention to the very high order moments. The simplest thing to do is to write down the average of the first moment, the second moment, which will be the Reynolds stress term, which is very important, of course, and we need to know, and then the triple moment and so on, which this is also a triple moment. And the question is, of course, we have a closure needing to know ever higher moments from the ones preceding it. To talk a little bit about what constraints we want on series, we can list these here. And the second one, this one, it should be expressed from the physical space. In other words, we always have in mind going back to the engineering problem and then being able to express what we're talking about in terms of rather wave numbers, which is just a technical way of doing calculations, in terms of the physical variables which we use in describing real flows. So there should be, of course, energy conservation. And the simplest possible thing to do is to set this triple moment, the fluctuating part of it, just equal to 0, in which case the average of the x, the total x, which I denote by capital X, is just equal to the average of x, like the average temperature, and the average of the products of two x's, which would be, let's say, the Reynolds stress or other kinds of terms like that. Then we wish to, if it's convection, to adhere to some thermodynamic limits, and this is not really obvious how such closures do when you treat convection, because you want the temperature to stay within its initial bounds, even though it's convected around and you're treating it by some kind of closure theory. So one example which took place long ago and was mentioned a couple of weeks ago in terms of maximum bound heat transport and such thing, is just to take the advection equation for the temperature and discard the triple moments, in which case we would suppress this term and part of this term, except the part that pertains to the interaction of the fluctuating velocity field with the mean temperature gradient in the vertical. So then let's see what happens, and it's interesting that if you do such a calculation, you get reasonable looking profiles for the mean temperature and the RMS or velocity field and temperature field, which is shown in these three graphs here, as going downward as the Rayleigh number increases. In fact, you get an estimate of the Nusselt number this way, which goes as roughly the 3/10 power of the Rayleigh number, which is not unreasonable. The coefficient we don't know, and this compares in some ways nicely with the experiments in large tanks, provided the aspect ratio is not too large. So that's to be kept in mind. The higher order moments, or really cumulates in this case, need not play an important role in estimating certain kinds of quantities. Although in the convection problem, it turns out that if we wish to look at the low Prandtl number regime, we are out of luck. So I want to mention a little bit about what happens, how is turbulence different from a random signal. So suppose we have a spectrum which is just Gaussian. and it consists of fluctuations. And suppose we apply to that case a Burger's equation at a short period of time. In other words, we have a pulse which looks like a Gaussian shape, and then we allow that to be self-advected by a short period of time. So in that case, we can ask, what is the hint of nonlinearity that shows up in such a problem? And it was pointed out long ago that if you have a signal and you suspect that signal is a product, at least in part, of a nonlinear term, then one thing to look at is just a triple moment where the x's are 3 different points in the homogeneous case, let's say. And then you see if this is vanishing or non-vanishing. Of course, if it's a Gaussian signal, this will be 0. But suppose we take that Gaussian signal and apply a little bit of this Burger's-like equation, and then look at what happens when you do that. You compute those kinds of averages, in this case with the random signal that you've generated with a bit of Gaussian, with a bit of a nonlinear term in it, and you get this kind of shape. And for a real turbulent simulation, you get this shape, which compares fairly favorably with the one above. So these are really bispectra, which are triple moments this way, constructed as a function of the time delay between in one direction and the second time delay in the other direction. In other words, you're plotting really the u at some point times u at another point times u of a third point, all collinear. And when you do that, you get this sort of shape in physical space. This is done with Bob Kerr's code some years ago with Olivier Mattei. And if you then go to trying to use a closure, and I'll come to that in a minute, but this is a particular simple wave number closure, which you've converted in this case to physical space, you get this kind of shape. And of course, this contains all in a triple moment information for homogeneous turbulence, and in particular, it contains the particular one which is proportional to skewness. And if you look at that in detail, you can make an expansions about the origin like this. This is the kind of quantity we're looking at, where x and y are just displacement coordinates along the same direction. They're not coordinates of space. So Yoshi Kimura expanded this about the origin in this way, and you finally obtain an expression like this. And here you see in front of it the skewness factors. So this is proportional to displacement cubed, as it should be, according to Kolmograph's third law. Here is the way it looks. So if you expand it about the origin, which is similar in a way to the ones we showed before, and that indicates, I think, that the kinds of theories we're going to describe are for this simple case of small nonlinearities, which exclude, I think, in some ways, coherent structures. It behaves properly. I want to mention now the original theory of Creighton a little bit, and try to see what kind of structure that theory is. So here we have, let's take a variable that's forced by a white noise random forcing, and let's try to see what we would do in terms of predicting its covariance as a function of time. And of course, if we introduce the solution at some time t prime into this equation, we can write the solution for the covariant very easily in this kind of form, where g is a known Green's function, which just inverts this operator here. If you go now to the case of fluid turbulence, you can make an argument in the following way. We replace the force here with a generalized force that depends on all the velocity fields in this fashion. And of course, in Navier-Stokes, it is kept incompressible by a non-local operator of that sort. And then we can try to choose, in this case, an eta, which preserves energy conservation in the presence of a Gaussian evaluation of this term. So we go through that process, and in fact, if you do that, you'll find almost uniquely what this gives is a direct interaction approximation. And then you have a choice of the Green's function. And to do that self-consistently, then you choose this so the flow would obey the fluctuation dissipation theorem in the absence of viscosity. But this turns out this way to be more general than the fluctuation dissipation theorem, and includes flows with viscous effects present. Now, when you do that in physical space, it becomes very complicated looking, several different lines to the equation. But you can try to make simple guesses for that solution. Suppose we, for example, replace these 2-time structures and 2-point structures by delta functions, functions of time and also of space. And this simply means that the covariance length scale and time scales are much smaller than the mean field length scales and time scales. And we get an equation of this form, where C sub s is a certain coefficient, which depends on exactly what the coefficients are here. Depends on the energy, kinetic energy, and the rate of dissipation of energy, like that. And you get a term which comes from computing the triple moment term, the fluctuating triple moment term, which looks like these 3 terms. Then you have other terms, which is the rapid distortion terms in terms of the energy of the mean field here, in terms of the Reynolds stresses, like that. So this is a proposal some years ago by Hanzalik and Launder as a part of the way to do boundary-free shear flows. I'm not sure how that's fared in the intervening years, but I just wanted to make contact with such engineering applications as what Launder and Hanzalik did. Now, somehow the division sign is absent occasionally in what I do, and I'm not sure why that's so, why it's absent sometimes and present at other times. So the hope is that if we replace this assumption here by something more realistic, then we will be able to generalize this equation by introducing non-local effects, which are well known to be important, especially in convection, and that way improve the engineering approach of this sort. That program is as yet unfinished, and I'll talk about why that's true in a minute. So the next point I want to mention is technical, and it has to do with these various theories that spin off of Creighton's original work, the direct interaction approximation, something called the EDQNM, or maybe it's NM, or MN, I'm not sure which. But Creighton proposed a theory very similar to that, perhaps a little bit more general, called the test field model. And both of these theories were constructed in such a way that they produce a K minus 5/3 energy spectrum for isotropic turbulence, not the K minus 3 halves, which eventually was shown to be a fault of the original direct interaction approximation. So why should we worry if the Reynolds number goes to 0 about such things? And what I want to point out is that if these are regarded as valid theories, then you should pick the one that certainly gives the best answer. And it turns out, in this case, at low Reynolds number, the direct interaction approximation is more accurate than these in an important way. And that's why we would worry about really certain aspect of the EDQNM, which has to do with the Markovian assumption that it makes in order to evaluate past history effects on the current state of velocity and temperature of field. I think this shows up in the decay of passive scalars at very low Prandtl number. This is something that Bob Kerr and I have looked at some years ago. And it also shows up perhaps in the evolution of the energy at small wave numbers. And at small wave numbers, as you recall, you expect to some extent the Lutziansky invariant to be preserved if you have a large box, or perhaps even an infinite Bach limit, and Peter Davison can tell you more about that than I know. In any case, that may be important because this theory, the EDQNM, has predicted a deviation from that result according to Lesieur and Schertzer some years ago. So it's an important quantity in the evaluation of theories as they provide realism for constraints on isotropic flows at large and even small Reynolds numbers, because the Lotziansky invariant should hold despite the large value of viscosity. It's something that goes through even in that case, as I understand it. So here a plot for very low Reynolds number, and this, I'm sorry this is blurred. This compares the skewness factor, the thing that we were talking about in terms of the triple moments, the derivative of the velocity field along a certain direction, and then you cube it, and then take an average, and that plays a role of the cumulative transfer of high energy to high wave numbers in the spectral space. So this compares some numerical calculations with data of Townsend and Traviolis. I think, is that the way you pronounce his name? Close. Anyway, this goes down, and Stan Corson said this is the lowest Reynolds number anyone ever looked at in terms of that paper. And so it goes down to a Reynolds number of 1. And here's the data. It's just not too scattered. Then it goes up to very high Reynolds number at the top end. In any case, I plot two curves. One is the direct interaction approximation, which is this one that falls off too low at high Reynolds numbers. And the other is a test field model, which is this right here with the Markovian approximation to the DIA. And you see, according to the points, if we accept this as truth, these points here, here, and here are Kerr simulation. So the DIA in that case preserves a good evaluation of the skewness at very low Reynolds numbers. And it's because the flow is decaying very rapidly in the final period of decay, and yet the theory is able to take memory effects of how the flow at the current state remembers its past history much more accurately than the EDQNM or the test field model for that case. I want to talk now a little bit about some failures of such closure theories, or perhaps failures. And the first point I want to make is what happens in the dissipation range of the turbulence when the energy spectrum falls off very rapidly, exponentially perhaps, as a function of wave number. And there was a prediction early on by Craikman that in that case the energy should fall off like an exponential factor. There are earlier predictions by Quo and others that it would fall off according to a certain power of K over KD, which is 2/3 of some value like that, and I won't discuss that anymore. In any case, this is a prediction of the direct interaction approximation, and also of those other theories, EDQNM and the test field model. And I want to refer first to this equation. If you look at this, suppose you're in a range of wave number where the viscosity is K is so large that no matter how small the viscosity is, this term is very important. If you look at the literature, you find that if you make an analysis of which terms in this equation are important, you're balancing the viscous term against nonlinear terms. And the time derivative plays a parametric role actually in that case. So in that case, you have really almost an algebraic equation to solve. It's very, very complicated because you have all these modes excited and they are interacting simultaneously. So I forgot the U in this case equation I see, so you should add that in. So that is a candidate for very intermittent kinds of flow. Frisch used to make this point some years ago, that if you just have an algebraic system, nonlinear algebraic system, and ask for its distribution function, it's going to be in some ways extremely spiky. So you're not going to be able to argue about weakly non-Gaussian systems of the sort that we were really outlining in the DIA and the test field model. So here is a result of calculation done by Shi Chen's group at Los Alamos. And this shows the actual fall off of the energy spectrum in the far dissipation range. You'll notice, and this is a direct interaction approximation. Now, you're going maybe a factor 10 or 100 above the Kolmogorov wave number. So you're deep in the dissipation range, and you'll see actually the theory here, the dashed line, and the simulation agree rather well out to several Kolmogorov length scales. And that was pointed out really in Creighton's original paper in 1963, I believe, on the Lagrangian history, direct interaction approximation, which was an approximation designed to capture the random Galilean transformation property that the other theories, like the direct interaction approximation, did not hold. So that's one point. We have, in terms of the DIA, the similar slope as the experiment, but a factor of 2 or 3 at least overestimate of the exponential coefficient in the equations that we were looking at, which are here. In other words, we're picking up a value of C, which is large by a factor of 2 or 3. So when you put that in an exponential fall off, you diverge pretty quickly as you go out to higher and higher wave numbers. So that's one point. And then the other point to make is that when you average this is done at 512 cubed, which is, I suppose, in 1962 or 3. And when you, if you look at the flow, pardon?
1992 or 3.
What did I say?
62.
Okay, 92 and 93, right. Thank you. So when you look at these curves and you suppose you subdivide the volume of space in which you're taking an average to get the energy spectra into, let's say, 64 smaller boxes within, so you cover the whole range of volume, but you have, you now look at averages over these sub-regions, which will identify which region is intense in its fluctuations and which regions are empty of much fluctuation. So when you do that, you can read here that you get, for the average value, a value of the average box size, a value which is rather close to the direct interaction approximation for a rather long way. And so what you see in this case is a result of strong fluctuations and then empty volumes where nothing much is happening. When you average over such a system, you're not going to get a good answer. That's the lesson, I think, to learn from that. So that pertains to the old saying that averages don't exist. In other words, the individual quantities you may average over, you may speak of averages if the averages are closely lying to each other, but if they're very far apart, then it doesn't make very much sense. And so here is an identification of those volumes where the fluctuations are strong, and they're plotted the very high derivatives of the velocity field in one direction, averaged or an absolute value, and you'll see, or not average, but just a spatial volume here, 2 different ways of viewing it, and you'll see places where the axial surfaces are twice the root RMS value are very spotty. And similarly, if you use a different filter, you get this very remarkably close shape for these things. These places where strong dissipation occurs are not vortex tubes. You can be ruled out by the shape of them. They tend to be edges of places where they're defined by blobs, which are similar in shape to these kinds of shapes here. So
is this a calculation done using a ordinary Newtonian viscosity?
Yes.
And I can't read the power. It says nabla to the something down there.
This is 8th, I think.
8th.
Yeah. He wanted to find very strong, identify very strong fluctuations of the mean.
How is the resolution?
Pardon?
Number of grid point or diameter?
It was
No.
512 cubed,
512
12,
cubed.
12 cubed,
It
so it's,
depends on which calculation.
it could be done at much higher resolution now, but,
Yeah.
so it was also,
How large the K max theta? K max.
yes,
How large in terms of eta?
oh, here, it's,
In the
case,
simulation.
yeah, the dissipation range begins, well,
In the
chromograph wave numbers right in here.
DNS.
Yeah,
How
and
much is K max theta?
120, I think this is raw wave number, so yeah. They plotted as,
So it's how do you remember how large the Reynolds number?
the Reynolds number, 18. It's very low, so one thing I should add is, we were challenged by a referee that we're not talking about high Reynolds number flows at all, and no, but this was the best they could do at 512 cubed if you wanted to look at the far dissipation range where this exponential decay of,
K max is about 10 eta.
yes, here.
Okay. About 10.
Yeah, here's K max, roughly here. And K max then is, the cutoff wave number is there. Well, I guess it'd be higher for a 512 cubed. It would be half of that times 2/3 with the de-aliasing rule. In any case, that's the point I wanted to make about such flows, at least in the far dissipation range.
A question that could be asked if I had been doing this would have, and in retrospect, is I would have asked to see K to the 16 times the energy spectrum. Okay? Because that's what you're plotting there.
Yes.
And a peak of that, even for this low Reynolds number, could very well be right at your resolution. That might be what you're just getting, is the sort of the effects at high resolution. Hard to say.
Uh-huh. This falls off by a huge factor. The logarithm of the energy spectrum, it goes down to 30 orders of magnitude. You could also ask how accurate are numerical algorithms that compute things to 15 significant figures, or when you're using an IBM machine. So there are questions like that which are probably not fully answered. It should be repeated if it's of interest at higher Reynolds numbers, current DNS by Yukio or.
It was done by Schumacher recently.
Oh.
2000 grid point.
Oh.
2048. With K max theta up to 10 or so.
Oh yeah. Is it similar? The results similar? Or do you,
No, the slope depends on the Reynolds number.
on the Reynolds number?
Yeah. Could you go back again?
Yeah.
The factor, that one, K cube, the
Yes.
exponents are depending on Reynolds number, and C also depends on that.
I would like to see that because, yeah. Certainly
And they are concerned with the effect of K max
yes.
up to 10.
Yes.
And we did much higher Reynolds number.
Okay.
And the results too. Our simulation was up to K max theta equal 4.
Yes.
There's a 10, but Reynolds number is up to 60 or 500.
Okay.
Ours are up to 700 or so. So we observed Reynolds number dependence of the prefactor.
Okay. Lesser dependence on this prefactor.
The exponent 3 is not true for higher number.
That's very important. Right. That's very important.
The prefactor, the constant, there is some constant before K.
Yeah, yeah.
The prefactor and the exponent 3, 3, and
Yeah.
the constant C,
Yes.
all of them depend on the Reynolds number.
Right. Well, actually, this power in the numerical simulations, if you do RMS evaluation of it, is 3.3, I think. Right? But it's even more dependent on Reynolds number.
Depend on Reynolds number and
Okay.
approach to some constant at around infinity. It's okay. But
Okay.
the approach is very slow.
Very slow. And is it the the number to which it approaches is what? Is it 3 or 3.2?
No, very different value.
Very different value. I would like
But
to.
maybe it's not far dissipation range. It's close to dissipation.
Yes. Okay. You mean okay? You mean in
And by the way,
yes?
sorry,
No, no. No.
regarding the closure,
Yeah.
all the closure, including zero cumulative approximation, gives the same answers. All the closure.
Oh, you mean quasi-normal?
quasi-normal,
Yes.
MET,
I'm not-
Lagrangian, whatever the
Right.
closure meant.
I'm not surprised in a way because there the Green's function is just viscous Green's function because you're so far out in
Yes.
the dissipation range.
So all the spectral closure give
Give,
the same,
right.
as far as I remember.
Of course, in this range here, they may be different.
It's different, but
Yeah,
for dissipation range.
I'm not surprised in that result. You have that result. Actually, the DIA is rather difficult because
Yeah, so zero force cumulative is much easier.
Yeah. well, the other difficulty is you have to remember history of the system. So if you use single time closure quasi-normal, then that's rather easy. But if you use two time or something with two times in it, it becomes
But
tricky.
again, the G is
Yes.
dominated by viscous.
That's right.
So
Yes, certainly.
answer is the same.
But I was required to use two times by certain people we're working with here. Anyway, I'll skip that. I want to talk a little bit about isotropic turbulence in 2 dimensions because I think we're in worse shape there as so far with respect to these kinds of closures and the appearance of strong intermittency than in 3 dimensions where the results I was just talking about in the far dissipation range are perhaps not very important or very interesting to many people, we'll put it that way. And I have not worked in this field for some time, but the paper that Jeff Chasnoff presented at the APS meeting some years ago got me sort of excited by the results because his argument, numerically, at least at that time, was that the K was completely self-similar, and I'll show his results in a minute, but he was saying that they are self-similar even in the dissipation range, and that's important because if you, excuse me, this is sparkling. If you, that's important because if you look at Bachelor's theory, for example, and even these theories I've been talking about, like EDQNM, DIA, and so on, and I suppose it's also true for the RNG that Yukio has invented, which is a similar thing to the Lagrangian DIA, but less work, I think. If you use those theories, you get agreement with Bachelor's theory. And that is, well, I must make one point, though. When you do such, what I'm going to say is that for decaying two-dimensional turbulence, these theories don't really agree very well because of the intermittency effect, I believe. On the other hand, if the flow is stationarily maintained with random forcing, and then an inverse cascade and a forward cascade, these two gentlemen, Foisse and Shea, have proposed that they have proved, in fact, that this spectrum K minus 5/3, K minus 3, which is essentially invented by Creighton, is in fact accurate. There is perhaps a logarithmic correction to this at high wave numbers, but it's not terribly important. And that paper is cited here. I haven't seen a reviewed paper on this topic, so I don't know where this proposal wound up in the mathematical literature. Well, let me go back then to the decaying two-dimensional turbulence. And I think most people would agree, and perhaps Peter and other people would contradict me, please do if you don't find it so, that the flow is nearly self-similar in all wave numbers. That was interesting because you can take these theories, the EDQNM and other theories like it, in 3 dimensions and show that they agree with the self-similar decay. It's not usually obtained, certainly in the experiments, because the in that case, the spectrum at low wave number goes like k to the first power. And this was an earlier result, which even that was analyzed, I think, by Chandrasekhar and others. And it used all sorts of theories, give the same answer. For example, Heisenberg's theory and other things still preserve this property that the spectrum at low wave numbers go as a k to the first power. Excuse me for a second. And that's a problem because if the spectrum goes like k to the first power, how does a modal spectrum, which is dividing the spectrum by k squared, that really gives you what the covariances look like at low wave numbers. That blows up. So what do you do in that case? And that question was never, as far as I know, raised in an important way in early days of solving these closure equations. Certainly wasn't true, and I don't remember that Chandrasekhar raised that point. And in fact, when Creighton originally did his calculations of the DIA, he substituted in his equations a spectrum like that, reasoning that that flow has a constant Reynolds number. So what do you pick for a Reynolds number if you want to compare with theories, or if you want to compare your theory with the experiment? So he picked one that would go as a constant Reynolds number, and as time goes on. So that was proposed and used several times until, let's say, the mid-60s or so, when Marcel Lesueur and Daniel Scherzer began to look at spectra, deciding that the spectrum at low wave numbers should behave differently. And so at that point, people started switching to other kind of spectra at low wave numbers. K squared is one that's preferred many times. In fact, it's hard to escape from a K squared spectrum if you use inadequate resolution. If you use very good resolution, then the spectrum goes like K fourth. And Peter and Yukio have analyzed such cases. In any case, if this spectrum U becomes self-similar, you can simply take this equation. It's a self-similar decay, and you can make the energy conserved in 2 dimensions, and then the entropy does what it wants, and then put that into the closure theory and crank out the answer for the coefficient A of t and lambda of t. And when you do that, you discover you run into an impossible situation, and I'm not going into the detail, but it just can't be done according to these closures, mainly because of these 2 conservation laws in 2 dimensions, whereas you don't have such conservation restriction in 3D. So what do you do? Well, first of all, you can show that if you relax the condition that the self-similarity pertains to both to the energy range and to the dissipation range, then you predict Batchelor's law. The entropy decays like T minus 2, which used to make people happy. For example, it's still, I think, I'm not sure how Marcel Lesueur feels about it still, but he used to violently object when you proposed any other kind of decay law for the entropy. Well, this kind of analysis of spectra was in C.C. Lin's book. I guess it's 1963. He's not quite that. So what's the problem? And here you state the problem is just the entropy decays like T minus 2. I think the problem is really the same as occurred in 3 dimensions in the far dissipation range. I'll show some pictures later, but you all are familiar with the people here who have worked on this much more seriously than I, that the flows evolve into well-separated vortex structures where in between them there's very little identifiable activity when you at least look at the vorticity structures and the associated entropy. So we wrote something about this some years ago. I think it was just after I was here the last time, 10 years ago. So it's published there in a volume. And that's a conference proceedings, and then we published it again in another conference proceedings, a slightly different take on the problem. And then I became worried, and I think Jeff Chasnoff did too, because the spatial scales of the flow, instead of going like the square root of time, behave like the t to the 0.4 power. And I don't know what to make of powers like that. I mean, it's 4 over 10, but of course, but how does that fit in with any kind of boundary layer analysis or whatever? I think, well, I'll come to that in a minute, but anyway, we in that paper I referred to earlier, we proposed a modification of modification of the test field model, or EDQ&M, which would make the system self-similar in the dissipation range, the energy containing range, and also in the entropy containing range, and applied that to the theory. And we got here's a test field model result here. As time goes on, you see it doesn't really obtain self-similarity. It simply goes to this state here, and these lines thicken as time goes on in such a way that you can't superpose them, especially in the dissipation range. And here, if you use a revised theory at various same times as here, you see quite good agreement as high wave numbers in the dissipation range. And then there begins to be a deviation from that at low wave numbers, but you're beginning to run into the boundary of the box in terms of representing large scale structures. You don't go back in any way to very low wave numbers in an accurate way. So this issue was unresolved, and I hope that people here can point out the kinds of errors that may lead to. What I interpreted this to mean is that the small scales are glued to the large scales in some sense, as they are not glued in 3 dimensions. In other words, you have long stringy vortex filaments, and these vortex filaments have the same time scale as the vortex itself. They're just a part of the whole structure. And when you do that, you run into contradictions with these theories. These theories assume in some way that there's a statistical decoupling of large and small scales. It's an idea that you inherit from the cascade of turbulence in the inertial range. Apparently it's not so here, so that's my take on it at least. So anyway, if you then look at the polyntropy structures, in other words, this shows the development of not the entropy, but the polyntropy, and they're associated. The vortex structures would be here, for example. This is a calculation by Yoshi Kimura, published in JFM maybe 5 or 6 years ago. You see then vortex structures here, and then spinning off of those, this quadrupole structure for polyntropy corresponds to elliptical structures for the vortex elements themselves. So they're spinning around. They become circular, as Nick Williams and others have shown. As time goes on, if they're isolated, but if they're not isolated, if they're embedded as a network of other vortices, then they spin off these polyntropy structures, which are the stringy regions, which we interpreted as the regions where the turbulence really exists. That's where entropy transfer is preceding, whereas in these elements here, these are essentially becoming inert as they become more and more circular. So they are really like black holes. It just simply exist without interacting with the surroundings. So that was the interpretation, and our feeling is that this is a picture of where the turbulence occurs, blue and red, and yet the green is the dominant spatial characteristic of this structure. And you're now going to take an average of this thing and talk about how the average property behaves, and you're not going into much detail in terms of what the dynamics is between those interactions. And it's certainly true that these kind of closures leave that out. And so that's the problem that such theories have. And I think I'll stop there with the conclusion. So we started by looking at isotropic turbulence. Why did we study them? And they seem to be the simplest thing to look at. And it's sort of like the guy who loses his keys in the dark, and he looks for them under the lamppost. So because that's the easiest place to find, or to look, or at least he won't necessarily find them. But I think the things that we've discovered, even by examining isotropic case, are much more interesting than our original question. So the other thing is that strong intermittency, and people here can tell you much more about that than I do. Strong intermittency means nearly empty regions, and then regions of intense activity, and we shouldn't average over such thing. And the major issue is, how do you construct a theory that does this? What sort of analysis tools do you use if you want to use a kind of simple closure argument to obtain good results? I think Benzie once had a proposal for this some years ago, and it analyzed the vortex structures in a localized way. You want to isolate the regions where the vorticity and, in fact, the polarity is strong. And in cases like this, that's hard to do, I think. How are you going to construct averages around this, since they are stringy things that go over a major two-dimensional volume, but only over almost a single-dimensional structure? So I'll stop there. Thank you. Yes,
Can you go back to your previous image?
this thing.
Yeah, so I mean, the other thing that immediately strikes me in an image like that is that you see immediately the long filamentary structures or stress regions have a foot both at small and
That's
large
right.
scales.
That's right.
That's
That's
the
right.
stuff I'm talking about. You
Yeah.
cannot get
You can't get away from it.
separate. Yeah.
And I haven't analyzed three-dimensional simulations, but can you do this in 3 dimensions? I think you probably can talk about their isolation.
So in fact, no matter how large the scales get in 2 dimensions, you're going to have large stretched regions.
That's right.
On the scale of the largest structures, so you're never escaping this in 2 dimensions.
That's right.
Yeah. Very good point.
That's right.
So the conclusion from that is that probably the idea of two-dimensional homogeneous turbulence is an ill-defined idea. Is that really the message from this?
That's the message I would draw from it, yes.
Yeah.
Or at least you have to be very, very careful about how you make the presentation of your averaging.
But that goes for any very intermittent turbulence.
That's right, yeah. Also, I think in 3 dimensions in far dissipation range, probably even in the inertial range, the deviation from k minus 5/3 that Yukio finds may be an expression of that. I mean, I remember, and one question perhaps he could answer in the next 3 minutes is if you take averages over subvolumes, and suppose you focus on the regions where you have activity and eliminate the regions where you have emptiness, gaps in the turbulence, do you get the same spectra, spectra steeper than k minus 5/3 in those regions as well as in the average over the whole region? In other words, if you average over subregions, supposing you're at high enough Reynolds number, do you get the same spectra as averaging over the total region?
I don't know.
Very interesting. You're almost ready to do that at 4,000 cubed. And
You have to use wavelets to do that sort of thing.
yes,
Yeah.
well, Marie Farge will
We have
explain.
done web analysis, but not yet seen that answer to the question.
Yes,
Maybe it depends on the definition of active or.
that's right. It certainly does. And when you plot vorticity, you may get a different active region than you do when you plot strain or shear. So I don't know the answer. Yes.
Can I take you back to your 3D far dissipation range stuff? You said the closures all predicted, maybe Yukio did, all the same thing, which was a k cubed e to minus k form.
I said that, but he said it isn't true.
But the closures predicted.
Because
But Yukio still said that the DNS gave the e to minus k.
that's
rather,
right.
rather than the Gaussian
Yes.
fall off.
Yes,
Whereas individual structures would tend to give a Gaussian fall off of a given scale. So
right.
is it a kinematic effect of averaging over structures of many scale, or is the exponential fall off some dynamical effect? If you
Yeah, it's both because when you that exponential law obtains for the real average over the whole volume, whereas the slope, the exponential factor c becomes too small, too large rather, for the closure, which is a fault of its structure, and then it also coincides more or less, roughly speaking, with the subvolume averages, where you look at the you eliminate the strongest fluctuations and just focus on the ones which are smaller. So I'm not sure that answers your question, but would be my answer. Yeah.
So this exponential e to the minus k times the constant
Right.
is, I guess every theory gives that, and is that what you said?
I don't say every theory, but every spectral closure I know, including quasi-normal, DI, TFM, ENM, all of them have the same structure in the far dissipation range.
Yes.
And it's pretty well observed in the DNS,
Which one?
this kind of behavior,
Exponential rather than Gaussian.
exponential.
Yeah, go ahead.
Go back.
Isn't that almost inevitable if you believe that solutions are smooth? It's got to have an exponential tail on it.
No, but-
Fourier transform.
It could be Gaussian and
Yes.
that's-
Smooth
Yeah,
and
Gaussian.
periodic.
Gaussian.
No.
No,
If it's single structure.
So that's a rough field. It's a non-smooth
Well,
velocity.
yeah,
and
it's-
eventually it's smooth, I think, at very high wave numbers.
well, I'm
Viscous.
glad it's smooth, but I just wondered why it couldn't be e to the minus k squared, for example. I mean, it could.
That's
Yeah.
That was proposed, I think,
By
earlier.
tangent model,
Yeah.
that is
Or it
small
could be
eddies
minus k squared, yeah.
on the random
It could be e
strain.
to the minus
It
something.
gives Gaussian
Okay.
rather
Yeah.
than exponential.
Right,
So, but all the closure gives exponential.
right.
But when you average over many Gaussian effects, you're going to get an exponential if you
Yeah.
Is
preface
that,
it.
is
but
that
that's-
how,
but
is
that's-
that how it works?
But that's kinematic, it's not dynamic.
No, it's just an algebra of how to do steepest descent integrals. But
Oh, okay.
So
the
that's why
the other thing, in terms of these theories,
Yeah.
if you look at the, I'm sorry to say this, but KPQ interactions, the interacting wave numbers, they're flat triangles. So that is, you can talk yourself into the idea that they're very flat rather than equilateral triangles. So two sides almost coincide with hypotenuse, so to speak. And when you have an equation like that, an exponential will solve it. In other words, the product of two
Oh, okay, yeah.
it's that way.
Yeah, I see.
So since it's just averaging for many Gaussians, it's not surprising that all the closures give the same.
Well, that may be true. That's an experimental or observational fact too, because if you accept Townsend's view, which is very persuaded, which is very plausible, then yes, you use steepest descent and you evaluate the average over many, but you always get a Gaussian in that case.
In the framework of closure theory, if we assume interaction between very separated wave number is dominant, then we can get Gaussian. But if similar wave number interaction dominate with the triad interaction, then we get minus
I see.
exponential.
Okay.
Yes.
Is the same form, apart from the k cubed, expected in two-dimensional turbulence?
No, I don't know what it is. Do you know in 2 dimensions in dissipation?
I should know it because it's in a paper that we wrote.
There you go.
You still agree with yourself?
I know KIDA, I looked at it in 92, so we just popped it out of KIDA
Oh,
in a
okay.
paper in 1992, and we checked his results.
Oh, yeah.
I just couldn't remember whether it was k squared.
Now, that's
Gaussian,
interesting
or
because you
1K.
checked it with your
Yeah, we also
vertex
did,
element.
No, we did DNS.
DNS?
Yeah, David
Okay.
Stokes simulation,
Okay.
and we very, very carefully
Okay.
resolved the dissipation ranges. We were trying to check things having to do with constrophy. In fact, we were trying to resolve Laplacian and vorticity
Okay.
squared and trying to measure these things. And so we did have a good resolution of the dissipation range. And so we got a very good picture of what the constant was. And we felt, we were able to show that things are tending to a constant.
Yes.
I can't remember if it was Gaussian or exponential now. But
Oh,
I have a
okay.
result on that.
Okay.
in this
I'd like to
paper.
see
We have
that,
the
yeah.
result.
Yeah. Great. We should go, I guess, for